want to talk more about logarithmic functions. In particular, I want to talk about two things. How do you graph logarithmic functions, and how do you find the domain of a logarithmic function? So let's jump back in and let me refresh your memory about what the graph of a logarithmic function looks like. Recall that a logarithmic function is the inverse of our exponential function. So if I have y equals, or f of x equals 2 to the x, here's how the exponential function looks. And f inverse of x, our log of x base 2, is our inverse function, so it's a mirror image across the line y equals x. And notice some of the points that we have. We have 1, 0, 2, 1, 4, 2, 8, 3, right? If you put in the values of 2 and 4 and 8, you get integer values back out. So that's one reason those are nice points to plot. But in particular, look at our logarithmic function. The domain is 0 to infinity. The graph does not exist over here. And in fact, there's an asymptote right here. I didn't draw it in because it coincides with that y-axis. So you can't really see it if I drew the dashed line in. Let's compare this log of x base 2 to the next function. I just changed the base, and now look at our exponential equations. They're a little more extreme. I kept the scales the same so that you could see it. So now when you're talking about y equals, or f of x equals 10 to the x, it's a pretty steep graph compared to 2 to the x. But the general shape looks the same. Similarly, the logarithm graph looks the same. It still passes through the point 1, 0, but 10, 1 is a nice point to graph. And the next place where I would find another integer value when I evaluate the logarithm would be at 100. That's why you don't see that on this particular curve. But notice the general shape looks the same. The domain is 0 to infinity because the logarithmic function doesn't exist over here. There's a vertical asymptote here, and the graph goes through 1. So let me show you in general what the graph looks like for our logarithmic functions. If we have a logarithm, or y equals the log of x base b, and b is any value greater than 1, then our logarithmic function will look like this. It will be flatter or a little steeper depending on what your base is. And notice I put in here that if your base is b, at b, you would be at 1. Because the log of 3 base 3 is 1. The log of 7 base 7 is 1. The log of 11 base 11 is 1. The log of b base b is 1. Similarly, at b squared, whatever b might be, you'll be at 2. So those are a couple key points that you could graph depending on how precise your graph needed to be. So now let's sketch one. Let's sketch the graph of y equals the log of x minus 5 base 3. Now we know we have this base graph, and as with all functions, our transformations work the same way. As soon as you see instead of an x minus 5, I hope you recognize that's a horizontal shift to the right 5 units. So when I first see a logarithmic function, I'm thinking in my head, here's my base graph. I know it goes through 1. I have that idea in my head. But now I see I'm going to shift it right 5. So instead of having a vertical asymptote here at 0, I'm shifting right 5. 1, 2, 3, 4, 5. 5 is labeled right here. I'm going to draw in, as should you, when you shift a logarithmic function to the right or left and you have an asymptote that's not on that axis, make sure you draw it in. And instead of the x-intercept being 1, it got shifted over 5 units as well. So if we're at 1, we shift over 5, we're here at 6. We have that point. That's a very important point right there at 6. And now I could do a rough sketch. I know the graph looks like that. Done. Well, it could be done. It depends on what you needed this for. Often this is close enough. What if it needed to be a little more precise? Then we could pick some values and make it be a little bit nicer. So for example, we know in this graph over here, without being shifted, the log of 3 base 3 is equal to 1. Well, instead of being at 3, let's shift that right. 8 would be a nice value to substitute in. I'm talking about just essentially plotting a point and putting in 8. 3 would have been nice, but we shifted over 5 units, so 8 is a nice value to pop in. Notice 8 minus 5 is 3. The log of 3 base 3 is 1. So at 8, you're at 1. Well, my graph wasn't too bad. I have it just a little bit too high. And if you needed to further refine it, you could find another point over here. But this one is pretty good. Boy, I'm not going to even have to erase too much. It's almost right where I had it and coming down this direction. If I had used a different base like 5, then maybe I would have needed to have refined it a little bit more. I was sort of lucky that it was almost where it needed to be. Let's draw another one. Let's graph this one. Y equals 1 plus ln of x. Don't forget that this is our natural logarithm. That means our base is e. Remember, e is about 2.7. So its shape is almost identical to the previous one. That one had a base of 3. This has a base of 2.7. So the shape is almost identical. But now notice our transformation. We're shifting up 1. So in my head, before I get to that, I'm thinking about y equals ln of x. I think about that graph before I get to this function. I realize it goes through 1, going off in this direction with an asymptote right here. So now let's present our actual graph for this function. This is a key point often for the particular graph at 1, 0, but we have shifted up 1. So let's see, instead of graphing it at 1, 0, I would be at 1, 1, and I would make sure that point is very clear. And now I draw the same shape as I did before. You can refine your graph by plotting a point. If a quick sketch is all that's needed, I would consider this done. Notice the vertical asymptote is still on the y-axis. That's why I didn't draw it in. This point's really important. My general shape is right. And that's pretty good. If your teacher or the problem you're doing calls for a more precise graph, then plot another point. Let's move on to this one. Again, I see I have a logarithmic function. My base is 5, but still I consider this my general shape that I'm looking at. It's flattened out a little bit more than base 3, but essentially that same looking graph. That's what I would have if there were no negative. That's just y equals the log of x base 5. Just a quick sketch of it. Remember, a negative in front of the function means we reflect the graph across the line or across the x-axis. So let's do that. The point 1, 0 will stay right where it is. This point over here, right, is across the axis, so it comes down here. These points down here will come up here. So I have a graph that looks something like this. Notice I drew it in pencil. If you needed a rough sketch, consider it done. You need another point, I would plot something nice to find, like 5, put 5 in. The log of 5 base 5 is 1, that makes it negative. So if this is 1, 2, 3, 4, 5, at 5 I'd be at -1. And notice I didn't even have a scale on the y-axis. So here, I'll put a scale on here. We'll make this -1 right here. So at 5, we're at -1. So my graph would look like this. And it hugs the y-axis a little bit quicker than a base of 3. And I would present that as my graph. Let me erase what I had in pencil. And there's my logarithmic function. Let's do another one. For the next one, we're going to not only graph it, but we will also state the domain. So let's just come up with a quick sketch of this one. Again, I'm thinking about y equals the log of x base 2, and I'm thinking about this being my base graph. Now, because of the transformation, it has shifted left 4, right? Left 4 units. So I need everything to move left 4. So I pick this graph up, move it left, and put it back down. That includes the vertical asymptote. So instead of having a vertical asymptote at 0, I'm going to have the vertical asymptote at -4. Oops, there's an asymptote. I was about to put a point there. It's a vertical asymptote at -4. I'm just going to draw this in. We're just going to do a rough sketch this time. The x-intercept would be at 1. When we shift it left 4, we're at -3. Those are 2 key points, even a rough sketch that I would include. Include your asymptote and include that intercept. So now we can draw our sketch. And we have the graph of y equals the log of x plus 4 base 2. Now the second part said to state the domain. Now looking at our graph, notice it does not exist over here. The graph exists to the right of -4. So based on the look of the graph, we could say the domain is from -4. Notice we never actually hit -4 because there's a vertical asymptote there, so we exclude -4. And it heads to infinity. You can put in any number you'd like to the right of -4. Compare that to this equation. How would we get to this algebraically? Well, remember when you're taking the logarithm, the argument, that's this part, has to be positive. So we could have solved x plus 4 is greater than 0. Subtract 4, we get x is greater than -4, and that in interval notation is -4 to infinity. So we wouldn't have to look at the graph in order to come up with the domain if you recognize this is what's important. So let's do another problem and let's come up with the domain without graphing. Now, it certainly doesn't hurt anything to think about the graph, but let's just look at these. This one, we can, in fact, both of them will do it in a very similar way. When we're looking at a logarithm or a logarithmic function and you're asked for the domain, the big idea is that we make sure we're taking the log of a positive number. That means for this problem, x minus 23 needs to be greater than 0. We only want to substitute in numbers that would mean we're taking a log of a positive number. So when we add 23, we have x is greater than 23. So our domain is from 23 to infinity, and there's nothing more to it than that. Let's look at our next function. Notice it's a natural log, but the domains for a logarithmic function with a base e isn't any different than a function with a base 14 or a base 12 or a base 10. What the important part is we're taking the log of a positive number. What numbers would make 4x plus 11 be positive? What numbers would force that to be positive? And we solve the inequality. So we have 4x is greater than negative 11. So x must be greater than 11 fourths. So in interval notation, we're talking about numbers from negative 11 fourths to infinity. Let's look at another one. We're going to state the domain for this function. Remember, the domain deals with the input. What numbers are okay to substitute in here? This 2 and this 3 don't affect the domain at all. What's important is what numbers are acceptable to put in right here. What numbers will force 16 minus x to be a positive expression? And we solve that inequality. If I subtract 16, I have this. I'm dividing by negative 1. Don't forget, if you multiply or divide by negative 1, you turn that sign around. So that means that any number smaller than 16 can be substituted in. So 15 or 14 or 2 or even 15.9. But anything 16 or larger is not okay. So our domain is negative infinity up to 16. Let's do one more. And notice we didn't have to graph it to come up with the domain. And in fact, in the next one, we wouldn't even know what the graph looked like, perhaps. We'd have to do some other work to figure out what the graph looks like. But that wasn't the question. The question is, what is the domain? So I'm going to set the argument greater than 0. Remember our goal. What numbers will make this expression be positive? So we set up an inequality. And I like this one as a reminder of how to solve a polynomial inequality. Let's factor it. We have x minus 5 times x plus 3 is greater than 0. And sometimes when people are working with logarithms, they forget about their polynomial inequality strategy. Remember, we need to figure out where the product is positive, and we're going to do that by interval testing. Our critical values are 5 and negative 3, and our job is to determine whether the numbers in each interval make this product positive or whether they make it negative. So we pick a number to the right of 5, like 6. 6 makes this factor positive. 6 makes this expression positive. A positive times a positive is a positive. Pick a number between negative 3 and 5, like 0. 0 makes this negative. 0 makes this positive. Negative times a positive is a negative. Similarly, we test a number to the left of negative 3, like negative 10. Negative 10 would make this expression negative. Negative 10 would make this expression negative. Negative times negative is a positive. So we know the only acceptable numbers for this particular function are the numbers to the left of negative 3 and to the right of positive 5. And in fact, numbers between negative 3 and 5 are not acceptable in that function. They would be undefined. And you could test it, put a number in there, and you'll see it doesn't exist. It's not defined. So our domain is negative infinity to negative 3 union 5 to infinity. And I would encourage you to look at a computer program that graphs, like Desmos or a graphing calculator, and you could see that it will give you an empty part of the graph right here. In fact, I'm going to bring in this graphing calculator. Let's see if you can see it. I already have it programmed in with the function that we did. And I'm going to come in closer so you can see. We'll move this over a little bit so you can see what our domain was. And I'm going to graph it. And here's what I want you to notice. It's blank, and it's blank in between -3 and 5. There are no points on the curve between those. So I hope you'll go practice graphing some logarithmic functions, and you'll be able to find the domains of some functions as well.